Hi guys, it's Henry here, contacting you from quarantine. We're going to do a bit of probability. I'm going to be recording you some lessons on this because I think that this is where most people have got to um, in the scheme of work. Some of you might have already done the first couple of bits of this. I know my class haven't, so we're going to get going anyway. So this is chapter 6. I'm going to be writing with a pen on like a pad thing, so my handwriting might be a little bit bad at first. I'm still getting used to it. So this is chapter 6, probability distributions. So we're going to start off by looking at some probability distributions. Um, Probability distributions have a few definitions associated with them. They're quite a simple topic, as you'll see in a minute. So first thing we need to know about is what a random variable is. So a random variable is just an outcome that has an associated probability. So for example, we could roll a dice, and if we roll a dice, then it has an outcome as a probability of that happening. So a discrete random variable, you might recognize the word discrete here, is a variable where a list of possible numerical values can be made. So for example, if I roll a dice and I label the outcome of rolling a dice as being x, so we normally call the outcome of our discrete random variable a capital X, capital Y, capital Z, something like that. It's an outcome where a list of possible numerical values can be made. So for example, x1, when I roll a dice, will be the outcome of getting a 1. x2, when I roll a dice, will be the outcome of getting a 2, blah 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 blah. So this is kind of what we're talking about here, and what we would say is that the probability of x equaling, for example, x1 is a sixth. So simple little statement here. It looks a bit weird, it can be a bit confusing because we quite often use capital letters and lowercase letters of the same letter. But this is quite a simple statement really. It just says the probability that when I roll a dice I get a 1 is a sixth. So a probability distribution is where the sum of all probabilities of a discrete random variable's outcomes is 1. This is known as a probability distribution, and we can put this in a table, or we could do it as like a little bar graph with, like, we would do, let's see if I can make some axes here. So we would have the we'd have the, whatever. We'd have the outcomes listed here, and then we would have bars going upwards to represent their probabilities. So for a dice, these would all be the same height because they'd all be a sixth on the y-axis. So, right, just go to the next page. How do I do that? Okay, let's just go to like this for the minute. I need to figure this out a little bit more. It's a little bit different on my home computer to how it is in school. So this is a very simple example of this. This is if we roll a dice, exactly the simple situation I was just talking about, and we have x being the random variable. So possible outcomes, we would have small x being our outcomes, and then the probability that the outcome of our discrete random variable equals that particular x value. So our outcomes are 1, 2, 3, 4, 5, 6, and then we have a sixth, a sixth, a sixth. You can see where this is going. Sixth, a sixth. And then all of these will add up to 1 always. And you sometimes will get problems where like one of these is a k, and then you have to say, well, they all add up to 1, so this must be whatever the other stuff taken away from 1 gives you. It's quite simple. You'll have done these sorts of things at GCSE before. So I'm going to have to just go like this. Here's a little bit more of a difficult example. I mean, it should still be fairly simple. So we have the same outcome. We have x being our outcome, and we have the probability that x equals x here. So a four-sided dice, which is biased, has faces 1, 2, 3, and 4. The number on the bottommost face is modeled as the random variable. What is the value of k? So our outcomes are 1, 2, 3, and 4. And then we have that the probability that x equals k over x. So this is k divided by 1, because k over x in this case is k over 1. So we're just going to write that as k. This is k over 2, k over 3, and k over 4. And obviously, depending on the question, you could have a different algebraic expression here that tells you what you need to put in this. So find the value of k. Well, we're going to simply use our knowledge about probability, which is that all of these will add up to 1. So my working out for this would just be that k plus k over 2 plus k over 3 plus k over 4 equals 1. So I want to add all these up. So I'm going to do a bit of mental maths here. So we're going to have our lowest common multiple of all these things being 12, our lowest common multiple denominators. So this is 12k over 12. This is going to be 6k over 12. 4k over 12. And 3k over 12, which equals 1. So we add these all up, 12 plus 6, 18, 22, 25. So we've got 25 over 12 equals 1. Do we have k over 12, that is? So 25k equals 12, which means, oh shoot, I've done that wrong. Still a little bit getting used to doing this. So 25k over 12, which means k equals 12 over 25. So when we've done that, we have to give the probability distribution of x in a table form, which is also fairly simple, because now all we need to do is rewrite this, but we have to rewrite it with our k in. So this is just saying question B. We want to, let me just pull this little table I made earlier over just to save a little bit of time. So we have here, we have x, probability that x equals x, 1, 2, 3, 4, and then we have 12 over 25, k over 2, which is going to be 6 over 25, k over 3, 4 over 25, and then k over 4, 3 over 25. We can just check quickly if we add up all of the numerators. Do they add to 25? Because that will give us 1 in total, and the answer is yes, they do. So we know we've done that correctly. And then find the probability that x is greater than 2. So you have to be a little bit careful with these questions, because obviously they can be different. If they say greater than or equal to, that would include the 2. This does not. I keep pointing at this using the pen, but then I keep realizing that I've set the pen not to actually record itself. So here, if I just do a bit of highlighting, so this bit is just a greater than, not greater than or equal to. So the probability that x is greater than 2, the probability that x is greater than 2 is going to be 4 over 25 plus 3 over 25, which is 7 over 25. And then it's a similar situation for these ones. So if I wanted to do between 1 and 4, I would add together, if I wanted to do between 1 and 4 here, I would add together the 6 over 25 and 4 over 25, which would give me 10 over 25, and then obviously simplify that. It's quite a simple question. And then if I was doing greater than 4, well, are there any outcomes that are greater than 4? No. So I would say the probability that x is greater than 4 is going to be 0. So what do you do if you've got a bunch of unknowns? So if you have a bunch of unknowns, like in this question, you have to do like a little bit of thinking here. So this spinner is spun until it lands on a red, or has been spun 4 times in total. Find the probability distribution of the random variable s, the number of times the spinner is spun. So essentially there's 4 outcomes here. It could be spun once, twice, 3 or 4 times. So this is a discrete random variable because it is a numerical outcome. So if s is the outcome, we're going to start by thinking, well, what's the probability that s equals 1? So s equals 1 would be if it only spins once, i.e. it lands on the red the first time. So the probability of it landing on a red in the first outcome is going to be 2 out of 5. And we're going to carry on doing this, thinking about all of the other outcomes as well. So the probability that s equals 2 is going to be if it doesn't land on a red the first time, and then it lands on a red the second time. So not landing on a red the first time would be 3 out of 5, and then the second outcome being a red is 2 out of 5. We're going to multiply them because they are independent of each other. So that gives us 6 out of 25. And then the probability that s equals 3. It's the same story. So the first one is not a red. The second one is also not a red. And then the third one is a red. So 3 times 3 times 2, it's going to be, 3 times 3 times 2, it's going to be 9 times 2, which is 18, and then 5 cubed is 125. So we then want to think, well, it's going to stop after 4 spins. So the probability that s equals 4 is going to be 1 minus all of the other probabilities, okay, because it's 1, 2, 3 or 4. So we've got 1 minus 2 out of 5 plus 3 out of 5, 3 out of 5, 6 out of 25. Hang on, let me just get the rubber on the pen. There we go. 6 out of 25 plus 18 out of 125. So the outcome for this is 27 out of 125. So the probability distribution, if you're asked to find a probability distribution, this is basically saying you need to represent this as either a table or a graph of some form. Okay, so that's what we're looking at when we see this table. So we just need to draw a table with these 4 outcomes. Okay, so we're going to have our outcome, we're going to call it x, and then we're going to say that the probability distribution is the probability that s equals that outcome x. So if I draw my table here, I've got 4 outcomes. Ooh, it's a little bit wonky there. 1, 2, 3 and 4, representing the number of spins, and then I'm going to just have these probabilities listed in this. So it's 2 out of 5, 6 out of 25, 18 out of 120. 18 out of 125, and 27 out of 125. And you can check on your calculator, these do add up to 1. So we've again done it correctly. So at this point, I would suggest that you go and have a look in the textbook and you have a look at these questions. So these questions are basically the exam questions listed in the textbook. Okay? These are relatively simple questions, really, which is why I'd recommend that you just go straight to looking at some of the exam questions, because there are questions like this in the exam, and it's just good to practice them. So what I would suggest you do is pause the video now, have a go at doing these for half an hour or so, and then I've got 2 exam questions which we're going to look at. So, first exam question. So this is from the AS exam a couple of years ago, for 2018 exam. And this is part A of another question. So this is quite a simple topic, really. So you tend to see it as being part A, and then what happens is part B is a binomial question, which is what we're going to have a look at next in the next video I'll do. So again, what I suggest you do here is you think, well, this is worth 2 marks, so have a go at this question, and it shouldn't take you more than 2 minutes. It's about what we want to think for this. So give yourselves 2 minutes, have a quick go at it, and then I'm going to go through it now as well afterwards. So if you've had a bit of a go at that, I am going to now go through the question. So a random variable x represents the number that the spinner lands on after a single spin, outcomes being 1, 2, 3, or 4. The probability that x equals r is the same as the probability that x equals r plus 2. So for example, the probability that x equals 1 would be equivalent to the probability that x equals 3, because that's 2 more than 1. And r is equal to 1 and 2. So r being 1 and 2 doesn't mean there's only 2 outcomes. There's 4 outcomes, because we've been told there's 4 outcomes at the beginning of the question. But there's also, you can see that there must be 4 even if it didn't say that, because if r was 1, from the statement that we're given that the probability of r equals the probability of r plus 2 here, this would clearly imply that, well, there must be 2 other outcomes apart from these. So let's draw our table. We're going to have r, do it nice and big, so a bit less wonky, but maybe not. There we go. And then we're going to have probability that x equals r. So the probability that x equals r, where r is 1, 2, 3, and 4. X equals 2 is 0.35. Well, if the probability of r equals the probability that x equals r plus 2, that means that the probability of 2 must equal the probability of 4. So this is also 0.35. And then we can just think, well, these add up to 0.7, so these two must add up to 0.3, and because they are the same, we just half that to get 0.15 and 0.15. Do these all add up to 1? Yes, they do. So we've completed the question. Final question I want to have a look at here is this question. This question is actually from the full A level rather than just the AS level. Of course, I've written here large data set alert. So we often don't like the large data set because we have to remember a lot of information about it. As you can see in this question, it actually talks about cloud cover. So we have to have a little bit of understanding and remember what's in the large data set for this question. So see if you can do that. If you can't, maybe just go on your phone or laptop or whatever and Google large data set. It will be the first thing that comes up, and you can look up the information talking about cloud cover on the very first page. So it should take you about 3 minutes because there's 3 marks for this question. So write down a probability distribution for C. So cloud cover is actually measured, cloud cover here, this is measured in octars. So octars kind of makes you think about 8, and there's kind of 8 amounts of cloud cover. Okay, so you can have a cloud cover of 8 octars, which would be fully cloudy, or a cloud cover of 0 octars, which would be totally clear. The problem with this that I think makes it a little bit difficult is that octars immediately makes you think of 8, and so you might draw your table and do 1, 2, 3, 4, 5, 6, 7, 8. And that would be incorrect, because it is quite easy to forget that 0 is also an outcome for this. So there's actually 9 possible outcomes. So I'm going to use the mouse here to draw my table out so it's a little bit tidier. So I need to make my table, and it has to have 9 possible entries. So 1, 2, 3. Right, that has worked. 1, 2, 3. I'm just going to go back to doing my hand. 4, 5, 6, 7, 8, 9. So if my cloud cover, let's just call it little c, and then because we're talking about cloud cover C, we'll say the probability that capital C equals little c. We can have 0 cloud cover, 1 cloud cover, 2 cloud cover, 3, 4, or 8 octars worth, 5, 6, 7, 8, like this. 1, 2, 3, 4, 5, 6, 7, 8, 9 entries, because 0 is one of them. Well, we're writing down the probability distribution. It says it's uniform in the question. So uniform would imply that they all have the same outcome, which means they must be a ninth. Because if they're all the same and they all add up to 1, and there's 9 outcomes, is a ninth. So that's that. So I think a very common mistake when this question was done was actually saying it was an eighth and ignoring the 0. Using this model, find a probability that cloud cover is less than 50%. So 50% would be 4 here. So we want to know what is the probability for question B, the probability that C is less than 4. So less than 4, if I just highlight the outcomes for that, less than 4 is going to be these outcomes here. So this plus this plus this plus this, which is 4 ninths. Very easy piece of maths there. 4 ninths. So there you go. So that's the first little bit. I'm going to upload a video either later today or tomorrow morning or something about the binomial distribution. I hope these questions were useful. I'm going to put a link to this presentation in the description for the YouTube video, so you can access it and actually look at this. You'll be able to look at this presentation in your browser, or if you download the OneNote app, you'll actually be able to have a live updated version of it in the app on your phone. You might need to log in with your Woodhouse email address to get that. All the best. I hope that you're doing okay, and I will see you in the next video.